Good.
Excellent. That's great. Okay. Well, good afternoon, everyone, and thank you for the introduction, Stephen. Yes, we have known each other for quite a long time, haven't we? But as you say, gauging is the topic that I really got into kind of mid-career, and the issue really is that having got into gauging, it was one of those topics that everyone said it's really straightforward, really simple. But some 30 years on, I think that there isn't a day goes by without me actually learning something about it. There's some shall we say, detail that needs to be looked at. And as gauging progresses, so we actually learn more and more about the mathematics and the simulations that we have to do to, shall we say, minimize the amount of space we waste in the gauging process. If I take you back a little bit in terms of the history, when we first started gauging, it was largely about static envelopes and things like that. And effectively, you would recognize that we knew the size of the vehicle, we knew the size of a structure, and we allowed a big margin between the two for anything that might have happened, such as vehicles moving, tolerances, etc., and having a little bit of extra fat in it to make sure that we were, shall we say, covered everything. As progressively we've gone through this, we've learned more and more detail about the processes, learned how to calculate things that before we used to just put as an allowance, until we got to the point where gauging is an incredibly sophisticated topic. And the mathematics of modelling it has got a great deal of detail in it to accommodate the various things that we have to take into account, that we know we need to take into account, that allow us to run much, much closer to the limit than we've ever done before. And those of you who've got experience of working on the London Underground, for example, will know just how tight some of the clearances are in that environment, and that managing it using the techniques that we have these days is totally possible. And of course, the latest generation of trains we have in those environments are actually bigger than they've ever been, yet the infrastructure has stayed the same size. And that's really what we're trying to achieve, is we're actually trying to optimize the fit and make the best use of what infrastructure we have without unduly working on infrastructure when we come to upgrade and maintain our network. So today I want to talk about a topic called hysteresis, and it's something that anyone who's done any sort of work in mechanical engineering will probably be familiar with as a concept, but is probably asking the question, what's it mean in terms of gauging? So what I'd like to do today is go through a few slides with you to demonstrate what we mean by vehicle hysteresis in gauging and how it affects the gauging calculations that we do. You may not know it affects the gauging calculations we do, but believe me, it does underneath. And then at the end of it, to come up with some ideas that maybe look at how we might be able to make our gauging equation, as I tend to call it, far more efficient. So I'm going to start by taking you through the first slide, and really to take you through a few of the basic concepts of gauging. Now, these days we do our gauging dynamically, so we don't take the static envelope and just add a clearance to it. What we do is we work out the dynamic movements of the vehicle for both things like cant deficiency, cant excess, overthrow, etc. And we work on that as the basis so that we actually calculate the values rather than guessing them. Now, you've got two diagrams in front of you. On the left-hand side, you can see in light grey a static envelope of a vehicle sitting on a canted track. And what you can see in black is that when you put that vehicle on the canted track, it will actually lean in the direction of the force. It's quite simply because you've got forces acting on an inclined plane, therefore the vehicle will sway towards the inside of the curve if it's not moving. If you look at the diagram on the right, what you can see is that the vehicle will sway to the outside of the cant, or in fact the outside of the curve, and that's a result of the curving forces acting on the vehicle. So what we can see in this particular situation is that a vehicle that's stationary on canted track will lean inwards, and I assume inwards to the side of the inside of a curve here, because we're working on the basis that the curve will have cant on it. And in the case of the outside, that the vehicle will be swaying outside the curve as a result of its speed going around the curve. Now, I think those are two pretty understandable concepts that we've got in gauging, and most people are aware of that. And in fact, in the gauging calculation, what you'll be doing is you'll be looking at the speed of the vehicle, the installed cant, the radius, and you'll be able to calculate the cant deficiency of the vehicle. And by knowing the cant deficiency and speed, what you can actually work out is what the swept envelope will be. And the information on which we calculate that swept envelope is actually provided by vehicle manufacturers. So what they will say is on any given cant, be it cant excess or cant deficiency, that this is how much my vehicle will move in terms of lateral, roll and vertical. So that's the fairly straightforward part of gauging. So let's just have a look at the next slide, which shows you a vehicle on equilibrium cant. On the left-hand side, you can see a vehicle that's traveling at just the speed to make sure that there is no force to the outside and no force to the inside. It's called the equilibrium cant, and we've got a formula. And if I point you to British Railway Track, that good old go-to publication of the Permanent Way Institution, it'll give you a formula to work out what the equilibrium cant is for any given combination of curve and installed cant. Now, in that situation, there's no forces acting on the vehicle. So therefore, you would expect the static envelope and the swept envelope to be coincident from the point of view of a dynamics perspective. There may be an overthrow on it, but let's just ignore the overthrow for now. What we can say is the vehicle's in equilibrium and the cant seen by the vehicle is 0. So therefore, there should be no dynamic movement. Now, what I've drawn on the right-hand side of this is a graph that would be supplied by a manufacturer to say, this is how my vehicle behaves when it's traveling on curved track. Now, I think you can look at that graph and say that doesn't look quite right, and you'd be right to say so. And the reason that graph isn't quite right is because it includes a parameter in it that effectively we don't normally think about, and that is that when a vehicle is sitting on this equilibrium cant, it may have a residual movement on it. We used to call it locked in suspension movement, but actually what it's about is it's about the movement that's in the vehicle as a result of it actually having, shall we say, been in a situation where it's displaced and it's not sitting on no cant, but in actual fact, it's come from a position where it was on a cant. So the graph on the right hand side shows from 0 to 150 going upwards what that movement would be. And then on the downside of it, it shows for a cant excess, for example, of anything from minus 150 up to the first point on the graph, which doesn't happen to be 0. And the reason for that is according to the next slide. And I've called this Schrodinger's cant. Now, some of you will have heard of Schrodinger's cat, which is a well-known equation or well-known theory in quantum mechanics, where Schrodinger's cat can be in two states. It can be either dead or alive at the same time. And in this particular case, what we have is a graph which is shown as it's presented to us from the manufacturers of the vehicles on the left-hand side, but on the right-hand side is how we assume it to be. And I think you can see here that if you've got 0 cant, then there are two possible positions of that vehicle to be in, depending upon whether it's come from a curve that's either cant excess or whether it's come from a curve that's cant deficient. So we can see that there are actually two cants that can exist, or two movements that could exist at 0. And that gives us a bit of a dilemma really in our gauging calculations, because we have to say that in any given circumstance, which one actually applies. So we take that a stage further to our next graph, which I'm going to take you back to why that should be. And basic physics, some of you will remember your physics courses at school of an inclined plane with a block on it. And that is that you can put a block on an inclined plane and it won't move until you put a force on it, and then that causes the block to slide down the inclined plane. And the concepts involved in this are what are called static and dynamic friction. And the reason for it is that when you have two surfaces in contact with each other, there's a friction on it, which is a certain level. And that means that you can increase the force being applied on your block and it won't move up to a certain point. And then you get a breakout friction value that occurs, which means that the block will then continue to move. Now, if I go back in my presentation, which I think is that one, then effectively what we can see is, hopefully everyone can see my pointer on this particular screen, but effectively what we can see is that we get to our 0 point, but it may not suddenly drop down to 0. It may actually start to carry on along that line until we get to that breakout force, and then it will flick to the 0. So I go back to the slide that we have. So that's the concept of static and dynamic friction, and the reason why on our graph we actually have a value here which says that our vehicle is actually the cant is reducing on it, but we haven't got to the point at which the vehicle is going to actually flip to the other side. So what we have is a classic, what we class as hysteresis curve on our vehicle. And depending on which direction you are going on this curve depends upon the nature of how the vehicle will behave. And if we have a look at a vehicle that's on a cant deficient curve, shall we say 150 millimeter cant deficiency curve, and we start to go on the transition and reduce the cant deficiency, we go 150, 125, 100, 75, 50, 25, and we carry on, because until we get to the point at which we're below 0, the vehicle itself will stay locked in on that side of the movement. And we get to a certain point, which on this particular graph I've shown as being about 25 millimeters, then suddenly the vehicle will flip to the other side because the frictional force will have caused it to move in the other direction, and it goes in that direction. If we will then go the other way and say we're on a cant deficiency of 150 millimeters and go minus 125, minus 100, minus 75, minus 50, we've got to go to some cant deficiency, and in this case again I've shown it at 25 before it flips the other side. Now this is called the classic hysteresis curve, and you'll see it on so many things, and it applies on the vehicles as well. So what we can see is a vehicle comes off cant deficiency onto cant excess, and it's some way into that curve before it flips over, and then when it comes from cant excess to go into cant deficiency, it flips back again. Now, there's a whole series of things that cause that to happen. One is the roughness of the track, and if you have rougher track, believe it or not, the actual curve itself tends to be shorter, because the reason for this particular point here flipping over is because the force applied on the vehicle has exceeded the breakout friction. If you've actually got movement on the vehicle as a result of track roughness, it means that that force becomes less, so it could actually flip over much less. So on rougher track we might have a smaller hysteresis curve, and if we have perfect track we might find it goes further, because we've actually got to have the forces that cause the breakout friction to occur to flip us over from one side of the curve to the other. How do we apply this in terms of gauging itself? Well, actually we cheat a bit, because we don't actually know the information that we need to be able to calculate from this particular curve. We do not know the points at which the hysteresis breaks out, so we have to make certain assumptions. What we do is we actually look at it from the outside case of the curve perspective and the inside case of the curve perspective. And what we're doing, as you can see here, is we're ignoring the fact that the vehicle flips from one side to the other. What we're doing is we're assuming that the vehicle carries on without it actually flipping from one side to another. So when we look at the outside case of a curve, we're following this particular line here. And when we look at the inside case of the curve, we're looking at this particular line here. So in this particular case, what we're seeing is that we have quite a significant band that we don't know where the vehicle is, so we're actually taking it into account. So in terms of the way in which we apply hysteresis in terms of gauging now, we're using the information that we have and calculating inside and outside cases based upon our assumption that hysteresis doesn't actually occur and that the vehicle is always locked in either one direction or the other direction. Now, from my perspective, that's a very inefficient way of gauging, because if we were to take a situation, for example, where we've got a vehicle that's running on a 50mm cant excess, then we would see from this particular graph that we might have 20mm movement towards the outside of the curve, but in actual fact it could be 40mm movement to the inside of the curve. So we've got 60mm of uncertainty here. That means that we are overestimating the size of the swept envelope by 60mm. If we're overestimating the size of the swept envelope, that means that we're actually maintaining inefficiently. So we might actually be forced to do work on a platform or something like that that isn't necessary, for the simple reason that the situation that we've calculated is we haven't got the certainty to say that we know our vehicle will definitely move to that side of the track, that it'll flip from the outside to the inside at that particular point. And therefore, going forwards, I would like to see how we can actually predict much more effectively what that hysteresis is. And in all of the cases around here, and in the cases around here, to be able to remove that hysteresis, to say that we're not going to take into account of movements that we don't believe will happen. So let's just summarize what I've said on this topic in terms of how we model hysteresis. It's a very real effect, but we don't actually know the flip point that occurs on that hysteresis curve. So what we have to do is we have to apply the full hysteresis to the inside and outside cases, because that's the safest thing that we can do. We don't know how long it takes to shake out hysteresis. In other words, if my vehicle is running on track that it's come from a cant deficiency and it's now moved onto a slight cant excess, we don't know how far down the track it takes for that vehicle to shake the hysteresis out and for the vehicle to actually orientate itself to the inside of the curve. Various theories about how long that is, but on track that, for example, if you come off a cant deficient curve and go onto straight track, there's suggestions that it could be something like about 200 to 400 meters, and that hysteresis will shake out. But we actually do not know what that is, and it's something that can only be determined by experiment or by modeling to actually come up with additional parameters to determine how long that will be. Using that, we could actually work out how far we are from the end of the curve, if we're on straight track, for example, to see whether hysteresis should be present. Now, the biggest effect on this is actually on deflated suspensions, where we've got airbags that are not inflated. Now, this is one of my big bugbears, of course, is because how many of you actually are aware of how many times deflated suspensions actually occur? The answer is that they don't actually occur very often at all. And if they do occur, it's often because a vehicle has left a depot without the suspensions being inflated after maintenance. But that's actually a procedure that should be avoided, and we shouldn't be in a situation where we've actually got deflated suspensions on the network. But interestingly, on the basis that we might have a deflated suspension, people will be aware that there is a reduced clearance requirement for deflated suspensions instead of inflated suspensions that fundamentally reflect the risk that deflated suspensions don't occur very often at all. But to my mind, the biggest effect occurs on the deflated suspension, which is a situation that shouldn't occur for much of the time anyway. And I think there's other ways we can mitigate against deflated suspensions, but I'm just trying to make the point that the locked in suspension movement we get, the hysteresis, is bigger on the deflated suspensions. We're currently analysing deflated suspensions, and therefore in a lot of cases we're double counting something that isn't likely to happen. Hence we might find that we are analysing deflated suspensions, giving us a much bigger swept envelope than really exists, and then providing clearance to it and finding that we're providing that clearance to something that we don't need to. So my conclusion from this is that there could be a significant clearance benefit in knowing the full hysteresis curve. And looking forwards, what I hope is that we can see in future vehicle modelling that the data that we get from manufacturers to allow us to model the vehicle movements should include some element of what the hysteresis is, so that we can take it into account in moving forward from our traditional gauging analysis and giving us more space to work with and reducing our maintenance burden in those situations where we've got tight clearances. And that's really the end of my presentation. There is a paper, a white paper as it's called, on vehicle hysteresis, which I've put together, which has got a little bit more technical detail in it than I've just presented to you now. But I'm hoping that what I've given to you gives you an idea of a concept that we currently use, but something that we believe there is scope for improving in the future. So on that, what I'd like to do is see if there are any questions from anyone about the subject of vehicle suspension hysteresis. So thank you for the opportunity to present to you today. I'm very pleased to do this, as I always am when people ask me questions like this, and really it's over to the floor now. So thank you, everyone.
Thank you very much, David. So yes, please put your hand up using the reactions tab if you'd like to ask a question. With chairman's privilege, if I might, can I kick off the questioning, David?
You certainly may.
It's a fascinating insight into, I suppose, the detail of vehicle behavior, but it occurs to me that sort of the hysteresis will actually be a function of vehicle condition as well as vehicle design, because we all know that as things wear slightly, as they wear in, things like friction change, systems get less stiff, move more easily, and so we get to a position where the hysteresis is very much almost individual vehicle dependent within a class, within a type of vehicle, and so it becomes almost another maintenance parameter that a vehicle, if we do gauging to a particular set of measurements or assumptions about how hysteresis works, then we actually have to confirm that the vehicles on the network are actually behaving in the way or within the bounds that we've assumed. And I wondered whether you had discussions with rolling stock colleagues on how manageable that is as a sort of maintenance systems issue.
Yeah, thank you, Stephen. I mean, it's a very valid point, of course, because in all cases engaging, what we try and do is actually to take into account what could possibly go wrong, and there are a number of ways of taking into account what could possibly go wrong. The one that we've traditionally done is say, let's take everything going wrong together, adding it up and saying, what's the worst swept envelope that could come out of it? Now, that's the way we've done it for a long time. But actually squeezing those tolerances and things like that into much more numerate values is what's allowed us to go forward. But we still have to take into account what happens when things go wrong. We traditionally, we do look at the track as, for example, being in the worst possible condition. We're looking at track to say not what is it like today, but what could it be like before anyone's going to come in and do any maintenance to it. We also look at all of the individual tolerances and say, how do these stack up and what could go wrong? What's the worst position that we could be in? And take those into account as part of as I refer to, the gauging equation. So what we know is that if we do a gauging calculation by the traditional means, then we'll go out and we'll say, hang on a minute, we've just calculated that this vehicle can't go past this platform, but it's going past this platform and it doesn't have any issues. Now, the reason for that is quite simply because everything hasn't gone wrong. And there is a process which you'll be aware I'm passionate about, because I've been passionate about it for so long now, I've forgotten when I started being passionate about it. called probabilistic gauging, which effectively says, let's not believe everything will go wrong at the same time. Let's believe that things go wrong vaguely randomly, but looking at that not everything goes wrong at the same time, but statistically what's likely to go wrong at the same time is something else. Now that gives us some insight into the way in which we can actually get closer to the reality. And I don't believe that hysteresis is anything more than another parameter that we can include in the mix of things that we look at. Let's look at it a slightly different way. If we had a vehicle that is traveling on 150 millimeters cant deficiency, and we suddenly put it onto a track that's 150 millimeters cant excess. So imagine the situation of a vehicle that's running at maximum speed on a curve, 150 millimeters cant deficiency. You instantaneously stop it, and it's on a cant of installed cant of 150 millimeters. It will flip to the other side. That's a given. We know that because that you're bound to have increased put the force on it to increase the brake to go past the breakout force. So we know what the bounds of it are. What we now need to look at is how far can we bring this in to the point at which we say, actually, we're not certain about it, because along there somewhere is the limit that we can say no matter what the maintenance condition of this vehicle is, there is a point at which it flips over. And I think even getting to that point is a major advantage over where we are now, because, you know, if we're on track that is 150 millimeters cant excess with 150 millimeters cant deficiency on it, we should be able to work out what's happening, what the point is, without having to take into account a parameter that can't occur, for example. So I think there's a halfway stage down here where we treat it like any other parameter. We model what its bounds are, we work out what it should be, and then we gradually pull in as we get the experience of it. But I think, you know, it is like, as you say, it's one of these things that is going to be a variable. It's going to be specific to a vehicle. It's likely to be specific to a suspension condition. So, for example, deflated or inflated suspension. But once we've got that information, I think it's probably fair to say that we could come up with some reasonable bounds for it, which would stop us overestimating the swept envelope in a number of cases.
Thank you, David. Very comprehensive answer. Could I ask other attendees or others who are in the meeting, and do you have questions that you'd like to put to David?
Interesting responses. Have I bamboozled everyone with it?
I think you. Oh, yes, I've got somebody. Hold on.
Steve, it's Tim
Timothy Knight. Timothy, would you like to put your question to David? Switch your microphone on and put your question to David directly, please.
Yeah, sure. Hi, David. It was just picking up on your point about roughness of the track. So yes. Are we saying here that the wheel rail interface is also going to play a significant part in this transfer of the train from one side to another?
Yeah, interesting question. I mean, if I put it slightly differently, if you could imagine a vehicle that comes from a cant deficient situation onto straight track, and that vehicle has got hysteresis, I think you can see that the moment you get onto the bit of straight track, that it will still have the residual sway, the residual movement on it that it had as a result of being on the cant deficiency. As it then moves down that straight track, gradually what you'll find is that the roughness, the bounce of the vehicle will mean that the hysteresis that's locked in will gradually work its way out. If you were on a cant excess, it would work its way out slightly quicker. But the issue is that it's the disturbance to the vehicle, the forces that are causing it to bounce, to move around, that actually cause that movement to, shall we say, break out from what it was. And in that situation, yes, it'll be anything to do with causing the vehicle to go up and down. So it could be track roughness, it could be corrugation, it could be all sorts of things that are causing the vehicle to actually bounce around and effectively release the movement that's locked into the suspension at that particular point.
I think that answers where I was going with that. So it's about conservation of momentum, And yes, the wheel rail interface could have an effect on that.
Yes, it could. I mean, it's probably the one time when you can look at it and say corrugation is a good thing, which we don't often as engineers say that, do we?
No, I don't think I've ever heard anybody say that corrugation is a good thing, David. Well, that's a first in my career anyway. Yeah.
Yeah.
Any more questions? Feel free, if you don't want to voice your question, please feel free to put it into chat and I'll pass it on to David.
And we can take any slightly peripheral questions to it as well, I think. If the topic of hysteresis has stimulated some other thoughts in people's minds about, I always wanted to ask that, then you can always voice it and we'll see if we can come up with an answer to it.
Yes, Mark Stonewell. Mark, do you want to ask your question directly? Put your microphone on.
Yeah, it's Mark Stowell here.
Oh, Mark.
Hello, David. Slightly linked to the topic. I'm just interested on straight track where you do get sort of vehicle hunting.
Yes.
Is that, how is that taken account in the envelope? Is it purely, does it take the envelope as a sort of a complete cross section and move it, or does it take some sort of end throw into account as well?
Well, that's a very interesting question because it depends on the level of detail that we go into. If I look at it in simple terms, what we'd find is that the majority of the hunting behavior that we have of a vehicle would be taken into account by the movement tables. In other words, to look at the body and the standard deviation of movement of the body in terms of its lateral movement, we would expect the hunting to be taken into account of that. But there's also other parameters associated with it that we also have to consider. And if we start to get into the detail, one of the things that we recognize is as a vehicle is going around a curve, then we find that the bogie itself tends to adopt a certain behavior, a sort of yaw behavior in relation to the track. And we'll find that as you go around increasingly tighter curves, so the leading axle of a bogie tends to move towards the outside rail, and the inside, the trailing bogie tends to follow the track center line really, although when you get onto very tight track it moves towards the inside of the curve. And we get a strange relationship that comes out of the curving behavior, which says that the vehicle will wander with a different mean depending on the curvature, and that effectively the worst movement to the outside is usually on a curve of around about 200 meters, something like that. So the vehicle will move outwards. As your curve tightens up, it starts to move towards the outside. And then when you get to about 200 meters, the bogie starts to move inwards again. So we've not only got the hunting behavior to take into account, which is a movement about the mean line of that bogie, but it's also taking into account where the mean line actually is. And again, where the mean line is dependent upon whether you've got two bogies that are behaving the same. Yeah. Quite often now we have bogies that are different front to rear. So you might have a powered bogie on one axle and a non-powered bogie, one powered bogie and one non-powered bogie, for example, which behave differently. And then we have to take into account the potential yaw of the vehicle as a result of those two means being different. We have to take into account, for example, on the movement of the vehicle within the flangeway, whether we're getting flange contact, whether there's any wheel wear, whether there's any rail wear. And it's actually quite an interesting set of equations that we've got to work out where it should be. Now, in practice, what this means is that we're playing with something in the order of about 10 millimeters. That's the sort of level of movement that we're able to be clever over. And most vehicles these days, we've got a lot of information that says this is how we can calculate it. But the whole issue of how the vehicle curves is very definitely something that we take into account in the gauging equation. And it's something that in the past we've just said, oh yeah, well, we'll allow plus or minus 12 millimeters or something like that. Now we can be a lot more sophisticated over it. As a result of that, I think we're probably saving in a lot of cases 8 to 10 millimeters of potential movement that can't occur. It also brings in another point as well, and that is that we quite often say we need to take into account flange wear and wheel wear and rail wear. Now, the interesting thing is, what's the point of taking into account side wear on a rail on straight track? Because a vehicle is unlikely to be running anywhere near flange contact on straight track. If it is, we've got a real problem that's beyond this. So there are things like that that need to be taken into account as well. And all in all, it's quite a sophisticated subject. And again, one of the reasons why I find that I'm fascinated by this simple concept of gauging and remain so long past my sell-by date, simply because it's, every day you learn something more about it and you want to dig a little bit more. So thank you for raising that one. It's certainly an interesting issue, and I hope that's answered your question, Mark.
It has. Thanks for the expansive answer, and yeah, really, and how you delivered it passionately. Thank you. Thank you, David.
Thank you. Any more questions? Mark Ward. Yes, Mark.
Hi, David.
Hi, Mark. Good to see you.
That was very interesting. Thank you. Quick question for you. So, have we done much testing to see what this looks like across various different bogies? And also, have we done any testing that says this is what the hysteresis looks like for a brand new bogey versus a worn-in one?
I think the answer to that is that hysteresis at this stage is something that we've accepted occurs, but we haven't really done a great deal to actually say, how do we characterize it and take advantage of the fact that it's a variable that is in our interests? So if you go back to the days of BAS 501, where we first started modeling vehicle suspensions, there was always a parameter in the equation called C, which was the locked-in suspension movement. It was this mysterious parameter that said no matter what you're doing, you always take into account this parameter. In other words, there's always this value here. C was the locked-in suspension movement, was actually the hysteresis. So we've known about it forever, but we've never really taken it into account in terms of how we model it. We came across it, I think, in terms of when we started looking at the vehicle dynamics. It was this what happens at zero that really got us all thinking about it, and as a result of that, I don't believe we're the only people that take into account hysteresis by saying, well, all we can do is back project from the point at which it crosses the axis and work on the basis that there will always be a hysteresis to the outside or to the inside, even though we are confident that it doesn't exist all the way. So I think the answer is we haven't done a great deal of modelling on it. And I think what I'm proposing, Mark, is that it's one of those things that we should be looking at in terms of going forward and how our constant quest to try and get closer to the truth can actually be, is actually possible to get more out of. Because I think, as you saw from the graph that I showed on there, and that was real data, there was 60 millimeters to be gained in terms of a lateral movement, just by the fact that on this particular vehicle, the level of hysteresis was about 30 millimeters from the zero line. So there's something to be had there. Quite what that is from a point of view of how we go about it and how we quantify that, I think is something that the industry itself needs to take on board and ask the questions, try and get some answers to it. And if we realise as a result of that we've got something to be gained, then let's work at how we achieve it.
Yeah, it's interesting. I got in my head that the benefit really is when you introduce a new vehicle, because that's when you've got all of the design stuff in front of you, and you can do various tests on the bogies. But obviously you can't then model the effect of wear and tear on those bogies and how to keep them in that service life. So you would get if you tested them, you might get the new behaviours, but not the worn behaviour.
Yeah, although, I mean, again, we come down to this thing about testing and simulation. One of the things, of course, now is that we rely hugely on dynamic simulation to give us an indication of how the vehicle is going to behave when it's got worn parameters. And, going back to the previous discussion with Mark Stoll, the question of wear in terms of wheel profiles does mean that, for example, a worn wheel set actually stays on the track centre line more than a new wheel set does. Yeah. So we actually find that in the case of wheel wear, the tread wear, that we increase our conicity and therefore cut down our gauging movements as a vehicle wears. Now, we can predict these things and we can build them into the vehicle models. And I'd be very interested to hear if there's anyone from a vehicle manufacturer on the call to see whether the parameters that we're talking about here are something that they would model routinely within the shall we say the portfolio of information they provide, but just don't give it to us because it's not necessary for us to know, but they will know what happens as their suspension wears, as the suspension components stiffen up, as they get various things going towards the end of their specifications. Because I think that this is something that they probably would take into account, but just don't, if you like, don't provide the information on the gauging portfolio because we've never actually asked for it.
Yeah, we'd have to organise to take it into account as well, wouldn't we, with different software modifications?
Absolutely, but again, if you look at the assumptions that we make, I believe that the data that we provide in terms of putting it into the software, we only need a few more parameters that says this is the nature of the hysteresis, for which I believe pretty well anyone that's building gauging software would be able to take that into account, because at the moment they're making assumptions on the data that they've got based on extrapolating it backwards to say this is where we think it's going to go in areas that's not defined. All it does is give us a bit more information to put into that little equation.
Interesting. Okay, thank you.
Thanks, Mark.
Cheers.
Any more queries? Any more questions for David? No, you have an opportunity to talk to one of the world's gauging experts here. Come on, guys. Girls. Yeah.
Yeah.
David, one comment you made, which I sort of picked up on, was your side discussion about airbag suspension deflation.
Yes.
And how seldom it actually happens, and it sort of took me back to my time at TfL and London Underground.
Yes.
Looking at derailment risk.
Yes.
And we did with a guy called Andy Vickerstaff, who may or may not be on the call, I'm not sure, but we did a huge amount of work looking at what actually drives derailment risk.
Yes.
And one of the many criteria we had to take into consideration was suspension deflation.
Yes.
And in some instances, it actually becomes quite a risk, quite a controlling factor.
Yes.
And it struck me that if we actually better understood it and were able to identify it and sort of isolate it very quickly, should it ever happen, that
yes.
there is the scope for reducing maybe some of the extra bunts, the extra risk avoidance that we put into the system, yes. Because it has to cope with deflated, or it copes in theory with deflated suspensions.
Yeah, I mean that's a very valid point. I mean, clearly what happens is if you've got a deflated suspension, you've got a stiffer vehicle, and as we've learned from experience, that stiffer vehicles tend to come to grief when you've got changes of curvature. I mean, I think the classic cases where this was discovered on the early days of Heathrow Express, when some very stiff vehicles were introduced, and the derailments associated with those vehicles were directly put down to the harsh suspension stiffness that they had. But I think the point you're making is even more general than that, and that is that there are an awful lot of parameters that we don't really know about, that understanding them a little bit more would give us more, shall we say, the opportunity to, shall we say, not build risk mitigation measures into our system. Now, my experience is that I don't believe I've ever seen a case of an airbag that has actually burst. People tell me that there have been deflated airbags. My understanding is that in those situations there has been some other incident that has caused an airbag to deflate, such as it's been deliberately punctured or punctured as a result of something else. And it reminds me almost of a situation that I was asked to investigate once, where a car transporter train had scraped a load of cars on the bridge, going underneath a bridge. And when we looked into it in more detail, the piece of information that was missing was that the train had actually derailed when it went through the bridge. So, you know, you get this situation of what comes first, the airbag burst or the incident. And, you know, like in cars, you know, there has never yet been an incident of an airbag deflation that isn't associated with an accident, but you don't know which happened first. So, you know, did the airbag go off and you had the accident, or did you have the accident and the airbag go off? I think it's one of those real grey areas that we don't have any real statistics on. There's a lot of, shall we say, myth and legend about burst airbags, and therefore we've got this paranoia about the things. But my understanding is that there are so many mitigations in place already, such as, for example, warnings to a driver if an airbag is not inflated. That is something that originally used to be used to control the speed of the vehicle, but I recall that because it hadn't happened, that effectively that was written out of a number of the swept envelope calculations on the basis we assume that the vehicle will be traveling at full speed, and you know that the airbag deflation occurred at an instantaneous point. But you know, seriously, we don't know how many airbags deflate, so we take it into account. In our probabilistic assessments, we tend to look at it and say, well, let's assume that it'll be 1%. We know it's not that much, but that at least allows us to give us some sort of numeric criteria that we can put into it to say, if it happens in 1% of the of occasions, then we're at least taking into account, and instead of saying we'll allow 25 mil clearance to a deflated suspension vehicle, we'll carry on using a level of clearance, but we'll look at the risk of that happening and therefore come up with a numeric value. But there's so many other tolerances like that. And I'll give you another example. And this is a big one because we all know those people who are working on projects like Transpennine Route Upgrade will be aware just how much the cost of an upgrade project relates to getting freight containers through tunnels and through tight bridges. Well, one of the things that we have on freight containers is we have a 25mm tolerance in terms of where that container might be sitting on a wagon. Now, if you think of 25mm in terms of the clearances we're trying to achieve on some of our tunnels, that's a huge value to have. We've got it there because we've always said that's what it is, but I don't believe anyone has really done any measurement on it. And indeed, if it was such a significant measurement, you could look at it and say, perhaps we should have better fastenings on our wagons that don't have that tolerances, because it might save us billions of pounds in terms of our route upgrades going forward. My quest continues to make sure that we get all the parameters that we've got numerate and defined. And I think you've just picked on one that really, you know, we do need to know the nature of airbag failures. Do they occur in practice? Are they mitigated in a different place? In other words, you know, is one of the things to make sure it doesn't come out of the depot with the airbags isolated. That could be the big issue. You know, why should we control the network based upon avoidable incidents? Surely we should be looking at avoiding those incidents before they actually get as far as the network.
Thank you. Yes, some very good points there, David. Any more questions? Or indeed contributions?
Yeah, contributions are always welcome.
I'm sorry, David. They're proving to be. We've obviously answered all the queries, raised all the imaginative questions that we can.
It's all either that or it's a result of the stripes on my shirt being the opposite direction to the pixels on the camera or something, and people are entranced by it and, you know, totally hypnotized by it. I hadn't realized this when I put this shirt on, that it was actually had such an interesting aliasing effect in terms of pixels.
Yes. Well, I shall resist the temptation to demand that all attendees write me a paragraph on hysteresis to demonstrate that they've actually acquired the CPD that coming from.
Well, they probably acquired the CPD by downloading our vehicle suspension hysteresis white paper.
Ah, yes, right. Okay. Well, if there really are no more questions and no more contributions. Oh,
Mark's back again.
Back. Yes, Mark.
Hello. Thanks again. I guess what's the next step then? David, for this?
Well, I think like so many of these things, the first step is raising awareness of it. We've got so many things historically in terms of gauging where we've raised the awareness of an issue, and someone has felt it worthy to take it forward. And you know, the example of probabilistic gauging that I mentioned is something that, you know, having raised it, it went forward through various things like the VS-SIC. It got RSSB research done into it, and subsequently that's sort of working its way through the safety protocols now, so that we should have a live technique available before long. That's my hope anyway. And I think this, like another one, is if people believe that it's something that's worthy of taking forward, then it will probably go to something like the Vehicle Structures Systems Interface Committee, which would then, if you like, encourage further looking at it, which might be research, it might be getting manufacturers to comment. But the Vehicle Structures Systems Interface Committee is a forum where anyone in the industry can put a point through their own community and say, could we look at this? And for me, I'm certainly happy that it should go to the VS-SIC to say, let's have a look at it, and is it something we can do taking forward technically? And if that's the case and it's deemed to have legs to it, then what will happen is that if you like, the work will be done that says this is the information that manufacturers need to provide. Manufacturers will look and say whether they can provide it or not. And ultimately, there will be a relationship between the vehicle manufacturer and the people building gauging software like ourselves, that will say, okay, we'll include that parameter now, and you know, job done, and job's a good one. So I think that's probably the process we'll go through, Mark. So yeah, you know, depending on which community you work in, there will be someone who sits on the VS-SIC who you could go to and say, I think this is something worth looking at. And if we get a consensus of opinion that it's something worth doing, then we'll look at it, because you know, we're all out to try and make this industry more efficient, and this is obviously a way in which we could do that.
Yeah, you're absolutely right. I mean, we're nibbling away at these tolerances over years, and obviously the probabilistic approach is doing that. And then things like the class 153, 155, better understanding of that yes. vehicle, you know, yes. and the amount of platform work that's helped to get rid of. And we have to challenge ourselves to be more efficient as an industry and not spend billions, as you say, doing work that doesn't need to be done. So nibbling away at these, understanding these scientifically and in engineering terms is obviously key, but then it's driving it forward and nibbling away at these tolerances that aren't real. And
yeah, I mean, there's also the issue, Mark, that we have to face as an industry, and that is that people these days get worried about the risks that they're holding. And one of the changes I've observed over my career has been, if you like, the pragmatism that we've had in the past, that can look at something as an engineer and say we'll make a judgment on that, is being eroded by procedural things and possibly by lack of experience in some areas. So I think there's a duty on those of us who've got the experience to actually try and start educating people to understand what risks they're managing and look at how the system itself can tolerate us taking out tolerances. One of the things that frustrates me, of course, is you know, we look at, say, we're modeling vehicles better, we're getting closer to the truth, but we still can't get to the point where we say, well, we model a vehicle better, can we reduce our clearances that we require? Yeah. You know, we went through an issue when we went from the Railway Group Standard 8029 to 5212, where we looked at it and said, you know what, we're double counting vehicle suspension movements here. Yeah. And we took the vehicle suspension movements out of the clearance calculation and made sure that they were in the swept envelope calculation. The net result was, instead of having 100 millimeters movement always built into the clearance, then what we said is, in some cases, you're going to have less than 100 millimeters, so therefore there's a clearance benefit. And interestingly, in some cases, you're going to have slightly more, so actually we've got less clearance than we thought we had. But nevertheless, that was a brilliant move going forward, which could be done in an age when people said, actually, we understand that and we're going to take that into account. But these days, I'm afraid one of the problems we do have is that we can improve our calculation methods, but we sometimes get lost in the fact that the clearance value that we have is to cope with the things we don't know. Yes. And as we know more things, we have to take it out of that. And I think that's a fundamental cultural issue that we as an industry have got to tackle. And I'm not really sure how to tackle that, if I'm honest, because it relates to, if you like, an overall risk profile that people don't really know what the risk is. If I say to someone, what is the risk of a gauging incident, they can't tell me what the likelihood of something happening is. But if I say I'm going to reduce my clearance by a certain amount, then they can tell me how much I've increased the risk by, therefore it's unacceptable. So somehow or another, we have really got to get to terms with risk and understanding, really getting numerate in terms of saying gauging is a science, as Stephen mentioned. It's a science, and we take the laws of physics almost for granted. I mean, there's some people that don't believe in them. I think largely politicians, but I shouldn't say that. We've got to get numerate and start to look at that in terms of it is a science, and we're going to take into account properly.
David, I've now got 3 questions.
Right.
Last minute stuff. Graham Hutchison has put one on chat. To expand the point made about gauging software, typical gauging profiles at the moment, when provided, only include the cant radii of the profile previous and after the current profile. To gain the full benefit, would this have to be reviewed?
Well, that's very interesting. Shall we say, listen to this space, because one of the things I'm working on at the moment is actually that when we've got a structure, we've largely got the full geometry of the track, and one of the things that we at D-Gauge are working on at the moment is actually to look at how a vehicle progresses through a structure and ignoring the plus or minus radii that we have. That are really just looking forward and behind for 10 meters, but saying we actually know what the survey is for the whole structure. And for the most part, we can use that to advantage to actually calculate how we model vehicle behavior in transition curves. I did give a talk about transition modeling a while ago, and I think it's something that's going to come to the fore fairly shortly, because what we're finding is that being able to look almost 3-dimensionally rather than just looking ahead and behind a little bit is a far better way to go. And I think we've demonstrated fairly robustly that the method that was used in the radius 10 meters ahead, radius 10 meters behind is no longer really, it was fit for purpose in its day, which was to actually check what was actually to make sure we didn't knock door handles off at Waterloo Station. But now we've got to the point where we want to see what's happening on transition curves, things like that. It's actually a bit of a sort of sledgehammer to crack a nut type behavior, which we've also demonstrated in some situations, as I showed in my last presentation, doesn't actually show the full spectrum of movement, for example, on reverse curves. So I thoroughly agree with Graham that this has got to be looked at. It is actually being looked at, and we're probably about a couple of months too early to actually expose exactly what we're doing on that. But frankly, there is a lot of exciting stuff here that says we don't necessarily assume the world to be completely on circular curves. So I hope that answers.
That's something to look forward to then.
So
I've also got Rebecca Selleck, who would like to ask a question. Rebecca, would you like to unmute your mic and ask away?
Hi, thank you, Stephen.
Hello, Rebecca.
Hi, David. So the question I was wanted to ask really boils down to, mindful of time, would you come to a gauging seminar that I'm putting together with the Institution of Mechanical Engineers? Because I think that would be a very fruitful potential ground for discussing things like, okay, yes, I agree with you, the likelihood of suspension failures is way lower than 1%. But where are the significant things that would benefit the infrastructure gauging community that the rolling stock community might be able to provide? So that sort of have an exploration of that. Could we do that in a sort of PWI meets IMechE sort of space?
Yeah.
That was my thing. And then I had a specific comment. I'll put that in the chat about the where we're going in terms of slices, because we at Cordell are delivering the new railway gauging data solution, which will take over from the National Gauging Database in August. And there you will have the functionality, to Graham's question, of being able to click back through slices. So it's not just the one before and after. You'll be able to just go click on our system and see them.
Yeah, I mean, I think Graham's point was largely that at the moment the slice has only got knowledge of what's happening in front and behind it. And from that we deduce what the overthrows are, if you like, on a transition, and it's technically incorrect. Whereas what you're proposing, what I'm proposing, is that we've got the data backwards, forwards and behind it. Let's use it. That's really where we both are. In terms of the conference, yeah, let me know. And provided I'm in the country at the time, then I'm more than happy to talk about to involve in those sort of discussions. So, you know, yeah, I'm more than happy to.
Yeah, thanks, Rebecca. And let's have a chat about doing something jointly between the IMechE and the PWI on that. That sounds a really interesting topic.
Yeah,
that'd be great. Thank you.
Thank you. And then I've got a written question, David, from John Bilo, who asks, has anyone compared RILA data on the same section of track, but recorded from different vehicle types? I mean, that's an interesting.
That is an interesting one. I mean, what I'm hopeful of, to be absolutely honest, is that when we measure data with RILA, we do take into account where the track is, because largely any vehicle that's measuring structure profiles should also be measuring the rails at the same time and subtracting the vehicle movements from that. So we should actually have, if you like, a relationship between the two rails and the profile, as opposed to the vehicle that's carrying the system. I'm sure Rebecca will nod sagely on this one, on the basis that the fundamental of any gauging system is that we need to know where the rails are at the same time as we measure the profile.
Yeah. The first dibs on getting 3100 standard approval for your surveying equipment is that you identify the rail heads.
Yeah.
So irrespective of where it is you're coming from, whether you're a drone or wherever you are, you've got to find the rail heads, and then you do everything relative to that in the space. So that's the accuracy of your rail head detection is the first up, and then your relatives from there. So it really, you shouldn't be able to, it shouldn't affect the output, but whether you could take different samples, as John's almost suggesting, and say, could we use that to tell us something interesting, it's a slightly different question that might be worth addressing.
Yeah, I mean, you know, clearly from the point at which we're looking at, you know, whether there's hysteresis or not, whether there's wheel set movement or not, what we're trying to do with any of these measuring systems is to make sure that what we're getting is purely the relationship between the rail head and the vehicle. I think John's point is an interesting one from the point of view of, has anyone compared it? I'm not sure. That's possibly something that is beyond the scope of what we can talk about today. But I mean, theoretically, that there shouldn't be any difference. And I think realistically, you know, over the years, most people have worked really hard, even going back to the early days of structure gauging train, where light sources were used, you know, sort of halogen bulbs and looking at reflectivities of railheads, etc., etc. You know, the idea was to take out any of the movement of the vehicle so that you've got purely the relationship between the rails and the structure.
Okay. Right. Are there any final queries? I think we're about 4 minutes just past where we aim to be, but I think those last few questions were really quite interesting and worth hanging on for. So any last queries, last chance? Right. Well, in that case, I will thank you again, David, for a really interesting and stimulating discussion. Yet again, pushing the bounds, and good luck in getting rolling stock engineers and infrastructure engineers to take hysteresis seriously, and more importantly, to understand it in much more detail. I noticed Brian's joined us on camera. I wonder, is that a cue that you would like to say something, Brian?
No, I've just been listening intently all the way through, and fascinating. I just wanted to congratulate David on being the world expert, and I just love this extra link to this. And I just wanted to say, let's take it forward and carry on with it in our future sort of seminars and things going forward. So just want to say a big thank you, really, and keep up the good work. And I do love the one of my comments is I just love this link to the physics and the maths, and it really excites me because of the stuff we're doing with professional registration as well, to get people back to basic in maths and stuff and engineering, which is what I really like, you know. So
yeah.
Well done, David.
Thank you, Brian.
Thank you.
Okay. Well, thank you very much, and I'll draw the lunch and learn to a conclusion at that point.